Hello, everybody. These are our day 2 notes. This first page is meant as kind of a review and a warm up, so I'm gonna go through this quite quickly. So they give us a couple graphs here, and they want us to write the slope-intercept form of the line drawn on the scatter plot. So the scatter plot is this graph here we see on the right, and we can see we have a line. Slope-intercept form, that's y equals mx plus b, for all those who don't remember. But what we want with slope-intercept form is we need a slope, which we can find, and an intercept, which if I look a little bit closer at my y-axis here, I can't really see where this line intersects. And even making things more complicated, I have a truncated axis here. So I can't really use the graph to identify my y-intercept. So I'm going to have to use point slope form. So the way that works is y minus y1 equals m times x minus x1. This also comes from our slope formula. With some slight manipulation, we could find our slope formula to be y2 minus y1 over x2 minus x1. So why would we use that? Well, what do we have? We have 2 points right there and there. So we would find our slope. So let's just plug this directly into point slope form. I really do think that it's going to be helpful for us in the future. So I can pick either point I like. So I'm going to pick the first, the higher of the 2 points. So I'm going to say y minus 57.99 equals our slope. Let's write the whole thing out. 57.99 minus our y1, which is 57.06 all over x2 minus x1, 385 minus 326, all times x minus our x. We used 0.2, so let's make sure we make that 385. So if you wanted to, we could go from here and simplify. Obviously, this is not a super simple looking formula, but I think from there, you guys can make sense of it. The big thing here was to remember a couple of our line formulas. Part 2, we'll talk about in class. We're really just trying to compare the prediction that we saw on the scatter plot with the reality that we see on the left-hand graph. But let's jump into our proper notes here. In this section, we are talking entirely about rates of change. So, in a linear function, the rate of change is constant. It is called the slope. This is a word I know each and every one of you have heard before, and is calculated using a few different formulas. Generally, we use m to denote slope. There's a couple different ways. We saw the formula that I'm going to write out here, y2 minus y1 over x2 minus x1, where x1 comma y1 and x2 y2 are points on the line. So there's a couple different ways we think about slope. I personally, this is my preferred, it's less formulaic. That triangle, we call that a delta. So the delta represents the change. So delta y, we interpret as the change in y, and delta x, the change in x. There's a couple different ways we can think about slope. What we're going to deal with slope is really dealing with non-linear functions. All right, so in a nonlinear function, the rate of change is not constant, right? If it's nonlinear, we could have a quadratic, we could have an exponential. The points, so if we want to find the rate of change between 2 points, we find an average rate of change. And this behaves very similar to slope, but because we're not actually identifying a slope, we have to modify our formula a little bit. And the way we're going to do that is going to be the output of a point, of the second point, minus the output of the first point. So f of x2 minus f of x1, all over x2 minus x1. This is very similar to our slope formula, just replacing the f of x2 and f of x1 in for those y's. So let's work through one together, and then there'll be a couple examples that you'll try on your own. So example 1 here, they want us to calculate the average rate of change of a function between one x1 value and one x2 value. So I'm going to just write those down. X1 is 1, x2 is 3. What I need to find, if I want to use my formula from above, is f of x1 and f of x2. In other words, what are the outputs associated with those inputs? So f of x1, I'm going to take this value, 1, and plug it in for x. 1 squared is 1, minus 3 is negative 2. I'm going to do the same thing for finding f of x2. 3 squared is 9, minus 3 times 3 is 9 minus 9, or 0. So now I have all I need to find the average rate of change. I'm going to take 0 minus negative 2 divided by 3 minus 1. So I have 2 over 2. We're going to simplify our fraction. The average rate of change for this particular example is 1. So what I want you guys to go ahead now is to look at examples 2 and 3, and you're going to find the average rate of change for the given points. Remember, they will give us x1 and x2. We need to find f of x1 and f of x2. We're going to do that using each of the given formulas. You guys can go ahead and pause and work these problems out. I'm going to pause and do the same, and then we'll come back together and see how we did. All right, team, let's check our work on examples 2 and 3. So what you can see here is we have some different functions we're dealing with. I'm evaluating these in my head, but if you weren't sure how I got these numbers, f of x1 is really f of negative 1. So the way I found f of x1 is I took in my absolute value 3 times negative 1 minus 1 plus 8. So what I ended up with there is the absolute value of negative 4 plus 8, which is 4 plus 8, and that's where I'm getting that value of 12. What I'm doing to find f of x1 and f of x2 in both these examples is plugging them in to the given function. I can see here that once it's all said and done, I'm then just using that average rate of change or slope formula to plug in and evaluate. You can see on example 2, we end up with a slope of 5/3. Make sure you simplify your fraction and be careful with double negatives. Especially on example 3, where the numbers get a little harder to deal with and there's negatives everywhere. We just got to be careful. Just one thing I've done as an organizational thing here, whenever I'm subtracting a negative, I always like to see that double negative, and I separate it with parentheses. It just reminds me to not lose the minus and changing the sign. So I like using those parentheses just as an organizer, but that's just a personal preference. So let's move on to page 2. We're going to look at another type of average rate of change. We're going to talk about the visual element of an average rate of change. Well, here we can see, before we get into the diagram itself, the average rate of change between 2 points on a curve is called a secant line. And what we can do is we can basically connect 2 points on a graph and find the slope of the line connecting those 2 points. So let's go ahead and literally do that here. So we want to find the slope between when x is negative 4 and when x is positive 4. So what I'm going to do is I'm going to actually draw a line connecting those just so we can visualize what's going on. So we're going to draw a line connecting those 2 points from -4, 2 to +4, -3. Well, what we're going to do is just find the slope of that line. Well, we're just going to find the slope, and it's going to be the change in y over the change in x. How do we find the change in y? Well, we can take the output, y2 minus y1, and find the difference between them. Or we can take the difference between the inputs, x2 minus x1. In this case, this should feel familiar. We're going to go ahead and take -3 minus 2 and divide it by 4 minus -4, again with those parentheses. Simplifying this down, we will get -5/8, and that is the slope. We could count this the old-fashioned way. From +2, we go down 5 units. Right, this distance here. Well, that distance is 5. That's our delta y. This distance here, well, that's, this should be -5 because we're going downward. Sorry. And then because we're going to the right, our run here, our delta x is 8. And that's where our slope is coming from, right? Rise over run. I would say the most complicated thing we're going to find is something called the difference quotient, okay? And this is this allows for an arbitrary selection of your inputs and outputs. So the way our difference quotient looks, so here's the formula. It's f of x plus h minus f of x all over h. And this is the formula to memorize, to know, to use on a test, to use on the midterm or whatever. But I really want to take an opportunity here to just pause and explain what the heck this formula means. So the difference quotient, here's where we're going to start. We're going to start with an image from Desmos. So this is an image from Desmos, and as you can see here, we have a curve in blue, and then we have a secant line connecting those 2 points in red. So, so what we're really going to try to find is that secant line, which you may also notice about this diagram is that it doesn't have any values. So we don't really know what point is what. So what we do, and this is going to help us understand that difference quotient, is we just say, well, let's let this input be some arbitrary value, a. And I know that if I plug in a to my function, the output will be f of a. So I have a point. I've identified one point. And why did we use a? It's arbitrary. We don't know what that point is. Well, how far do we travel? Well, we travel some arbitrary distance. And this distance here is what we call h. So that would mean that this point up here, the input value would be a plus h, and the output value would be f of a plus h. So what we're effectively doing with the difference quotient is finding the slope between these 2 points. These 2 points where we basically know nothing about them. We say f of a plus h minus f of a all over a plus h minus a, which simplifies to f of a plus h minus f of a all over h. The slope of this secant line that we know basically nothing about can be found with this formula. That's what the difference quotient does. It allows us to find the slope at any given point on a curve if we know the first point A and the horizontal distance between the first point and the second point, h. All right, so let's try one example together. You'll try one on your own, and we'll be out of here. So here they give us a function, negative x squared plus 3, and they want us to simplify the difference quotient. So we're going to plug in to our formula, f of x plus h. Now remember, when we compose functions, we replace x with x plus h. So that's going to look like negative x plus h quantity squared plus 3 minus negative x squared plus 3 all over h. So as you can see, this isn't super useful at this point, so we need to simplify. We're going to start by simplifying our numerator. When we square a binomial like this, we are going to result in a trinomial. It's going to be negative x squared plus 2xh plus h squared plus 3, and then that whole quantity is subtracted, negative x squared plus 3 all over h. Now, what you'll notice happens here is a lot of our terms cancel out. I have a negative x squared, and I'm subtracting from that another x squared. I have a 3, and I'm subtracting 3. So what we're left with, and this will be our second to last step, is going to be negative 2xh minus h squared. I just distributed that negative sign all over h, and you can see here each term contains an h, so we can divide out. Our simplified difference quotient here will be negative 2x minus h. What that means, and this is the part that in the past I think we lose sight of. What that means is that if I want to find the slope between any 2 points on the function negative x squared plus 3, all I need to know is x, all I need to know is h. What h will give me, the horizontal distance between these 2 points, along with that starting x point, I can find the slope very simply. I don't need to plug in y2 and y1. I basically have simplified that y2 and y1 formula into something that I can just plug in and finalize. I know we're getting long here. I'd like you guys to try this last difference quotient on your own. This one's going to take a minute or two, but you can check your work against mine. I'm going to go ahead and pause as usual, and you guys can take a crack at it. All right, almost there. So they want us to find the difference quotient for f of x equals 2x squared minus 3x plus 5, when h does not equal 0. Now remember, that makes sense, right? We're trying to find the average rate of change between 2 points. H represents the horizontal distance on the graph between those 2 points. So if h equals 0, there's no distance between these 2 points, and they're not 2 points, they're just 1 point. So that's what that h does not equal 0 is really standing in for. So here you can see my steps here. I replaced x with x plus h on the left-hand side of my numerator. Make sure you're comfortable expanding binomials, right? That's something I'm expecting you to be able to do at this point, and then distribute that to n. In that second step, you can see I'm starting to cancel out some terms that show up in positive and negative places. So I have a 2x squared on the left, once I distribute that 2. And then over on the right-hand side, I have a negative 2x squared. Well, they cancel each other out. The negative 3x's cancel each other out, and the 5's cancel each other out. We're left with 4xh plus 2h squared minus 3h all over h. We can see that each of those terms can be simplified, and our difference quotient here is 4x plus 2h minus 3, and we are done. Nice work, everybody.